Cool. All right. I'll take that as an auspicious introduction. Are we recording? Did we?
Yes.
Yeah.
Okay, cool. I didn't see it on my screen, so okay.
I just pressed record, so go ahead.
And
Okay,
then if anybody is new to Talk Math with your friends, we ask that a couple of you leave your mics on and cameras on to be sort of the live audience, the featured friends. Andrew, did you identify and bring any featured friends with you?
I did not, although I tried my best on social media to boost the participants. So I didn't pick out anyone special. I love you all equally.
Well, can we get 3 people to volunteer to be the live audience, and I'll monitor the chat?
Yeah, I'll live audience.
Okay, we got Parker.
I can if you want.
Lauren, that'd be great. Thank you. Let's see.
I'd be happy to say things.
Can't tell who that was, but that'll be great.
That's me. I'm new.
Excellent. Welcome. All right.
Okay, cool. All right. So as I don't think I actually promised this, but Kate said that I did. Said I was going to talk about specifically juggling tanks. So I figured, here's a good place to start, right?
You totally said that.
I said it's like juggling, but well, okay. All right. Anyway, okay. I want to say, first of all, in the abstract, I called out Robert Carroll, who's at Illinois specifically, but I also want to point out on the math side, Radmila Stojanovic and Vin Da Silva of NC State and Pomona College, respectively. I wasn't able to find pictures of them juggling, but Vin's is pretty close. Okay.
That's a sweet author photo.
Isn't it? It's pretty great. Vin's a funny guy. All right, so I want to talk about configuration spaces, or talk about the juggling problem generally. So I'm going to start with space, which I'll call X. Okay. I don't care what X is. It could be lots of different things. By training, I prefer closed manifolds, but if you want to do this on an algebraic variety, no one's stopping you, or even a graph. So I want to think about what it means to juggle in X, right? So if I've got 3 balls, a red one, a green one, and a blue one. Oh, good, Drew, good. So a configuration is just going to be a list of the positions in X of these 3 balls. To make sense of juggling, you don't want to allow them to coincide, which means that your coordinates have to be distinct, right? So X red and X green have to be different, same with red and blue, and same with green and blue. You can do this in general, right? You just take the n-fold Cartesian product of X, and you cut out all of the diagonals where 2 of the 2 distinct coordinates are equal, right? So this was introduced in 1962, and some stuff was said about the topology of it as sort of its own object. Here's a picture of R3, so the configuration space of 3 points in the real line. You can see that you start with R3, right? The threefold Cartesian product, and you cut out all of these 3 planes because there's 3 ways that 2 of them could coincide. Okay, so that's what it looks like in general, right?
Wait, why are they all intersecting? Shouldn't they be like pairwise?
We've got 3 planes in. So what should the intersection be? It's where all 3 coordinates are the same. That's a line. Yeah.
Don't we? Oh yes. Okay. Sure. Oh, that's the stuff we're removing.
Yeah. So the picture that we're drawing. Yeah. Sorry, I should have said that. Yeah, thanks. These are the removed things, right? So it's everything else. It's R3 minus that is what we want.
And
right?
once you hit like that red plane, the balls run into each other and it's bad. Okay.
Exactly right. Yeah. So these planes are sort of where 2 balls are intersecting each other at the same time. Yeah. Crashing together. So these are the bad diagonals, as I will call them, right? Or the forbidden diagonals. Okay. So what does juggling look like? You need a path in this space, right? You need to keep all the balls in the air in such a way that they don't crash into each other. Really, we want a juggling rhythm, though. So we're going to think of this as a map from the circle. We want to be periodic in what we're doing. Probably, I only care about juggling rhythms up to homotopy. Yeah, if 2 juggling rhythms are, one can be deformed into the other continuously, I don't care about the difference between them. So I'm going to think about the fundamental group of this configuration space, right? That tells me how many distinct juggling rhythms there are in this space X. So can we have poll 1 now? Okay, so how many different juggling rhythms are there in ordinary Euclidean space of 3 dimensions? You're out there in space juggling like we are now. How many do you think there are? How many different ones?
while you're processing that poll, it's not clear to me why juggling is R into the configuration space. It's somehow more clear to me that a juggling rhythm is S1 into the configuration space, though.
Yeah, I'm just thinking of, I'm watching the balls over time. Yeah. So, that's T is just a time variable, right? As I'm watching them, they move, right? Yeah. Oh, does it matter how many balls? So let's see. Let's say for 3 balls. Yeah.
Oh, can we switch our answers now?
Well, I'm gonna say I think this is pretty good. Okay, so cool. So that's one question you can ask, and it comes down to what pi1 looks like. So it looks like most people thought there should be some finite number more than 2. The next one is infinitely many. So remember that, right? I don't know if I can leave the results up or not, but remember that. Okay, so the other question you can ask is a motion planning question. If I give you a configuration X, right? So the balls are in a certain position now, and I want to get to a certain position Y, can I do it, right? And that's just asking about whether or not this space is path connected. Usually these spaces, X is gonna be nice enough that everybody in sight has the property that connected and path connected mean the same thing, so I'm not gonna worry too much about that distinction. But you're just asking, is it path connected? Can I get from one configuration to another? Then you have another question, which is, supposing you could get from X to Y, how many different ways could you get from X to Y? And again, that's really asking about the fundamental group, right? Because 2 different ways of getting from X to Y are gonna constitute a loop in the space. Okay, so that's sort of why you should care about the topology of these spaces, right? Sort of where we start with. I want to talk about motion planning sort of in a little bit more generality, and I'll introduce the term global motion planner to be a continuous function that takes in 2 points in your space Z and spits you out a path in Z, and it's got to be a path that starts at A and ends at B. I want this to be continuous in the sense that if I wiggle the endpoints, I only wiggle the path a little bit. So you should think of this like in Euclidean space. If Z were Euclidean space, we all know a global motion planner. What is it? Somebody volunteer. If you 2 points in Euclidean space, how do I find a path between them?
Draw a line.
Draw a line, very good, right? And that's continuous, right? If I change the points a little bit, the thing only changes a little bit, right? There's no obstructions to that. So that's a global motion planner. Unfortunately, that's just about the only time you can do that. So you admit a global motion planner, there is such a function, if and only if Z is contractible. So completely topologically uninteresting spaces are the only ones that have global motion planners. And this is actually a really old theorem, and it's of Whitehead. I didn't get the date, but it's old. Okay, so the way I want to think about this theorem is saying that the topology of the configuration space measures the difficulty of juggling balls in that space. Right? If Xn were contractible, then you could, everything would go, right? You give me any 2 configurations, I can get right there and no problem, right? I can memorize exactly 1 rule, and that will allow me to juggle however I want. Okay. So now how do I measure topology? I like to compute homology rather than homotopy groups. This is Samuel Eilenberg, who has an understandable objection to this claim. Okay. All right. So I want to talk about the homology of configuration spaces. Actually, I'm going to talk about the cohomology because cohomology is always better than homology. So Arnold did this in the 60s, right? He computed the cohomology for the configuration space of endpoints in the plane, right? Which he thought of as the complex numbers. It's got a lot of generators. What are they? Well, if I have, let's say I have 4 balls, then I'm going to have 6 generators, right? So, well, I guess as I've written it here, I have a few more than that. But these generators have this nice properties. They square to 0. Omega ij equals omega ji, so you have a triangular number's worth of them. And they have this sort of cyclic permutation relationship. So if you overlap in 2, you overlap in 2, and you overlap in 2, and you cyclically permute, you add those all together, you get 0. Maybe the most important thing for us is that these generators all live in H1. They live in one-dimensional cohomology, which means, in particular, if you're trying to juggle on a tabletop, well, H1 is pretty big, which means pi1 has to be even bigger. Okay, so there's lots and lots of homotopy to go around. Okay, so there's lots of ways to do it. If you know what the braid group is, there's a relationship here. That's why Arnold was interested in this. So here's a picture of a pure braid. notice that each strand starts, they go, you read them left to right, they're red, green, blue, orange, and they're the same at the top and the bottom. So this is a pure braid. And you can imagine this as take horizontal slices of this braid. What are you going to see? You're going to see 4 colored points in the plane. And because it's a braid, they didn't hit each other. And the pure braid group is, the group of such things up to homotopy. So that's just pi1 of this configuration space. So that's, if you're interested in braid groups or braids or knots or anything, there's interesting relationships to that. Okay. What are some other? Go ahead.
Is there an opportunity for us to like beef up our intuition with the juggling analogy here by thinking of like a particular kind of juggling now?
Well, so this is juggling on a tabletop, right? So what we view the braid is like each of these horizontal things is a time slice. So like imagine that you're trying to juggle on a tabletop, and as you're juggling, the tabletop is moving up. Like it's moving vertically through space.
I was going to say, I might be able to help with this.
Sure.
In that you can think about the balls, actually, maybe the cup game even. I was going to say, take the balls and have them swap places with each other at various moments in time. And so then each of the slices looks like this, or like this, or like any of the corresponding configurations. And so things are swapping places?
Yeah. Awesome. Okay. So what are some other things you can say? If your original space, your base space, the place you're doing the juggling, is path connected and its dimension is at least 2, then the configuration space is path connected as well. So that answers the question of, can I do the juggling correctly? Right? Yes, I can. You give me 2 configurations, I can get from here to there. Turns out that if your space is simply connected, right? So your space itself doesn't have any interesting loops in it, and its dimension is 3 or greater. Let's say, so I'm saying dimension here, so I'm sort of specializing to the case where this is a manifold. But in that circumstance, actually pi1 is trivial, right? So what does that tell us about our answer to the quiz? If we take X to be Euclidean space of dimension 3, what do we know about how many different juggling rhythms there are? Somebody volunteer.
I guess there's just one.
There's just one. Yeah, which is kind of crazy, right? You imagine, what it says is if I'm juggling whatever school of juggling I went to and I learned how to juggle in a certain way, and you learned how to do it in a different way, there's like a path of jugglers, a continuous path of jugglers from me to you that allows me to deform my rhythm into your rhythm without any balls hitting each other.
That's sweet.
Like,
that's
to me,
very,
this
very
is
weird.
This is shocking to me, right? I was really shocked when I learned this. Okay, cool. Okay, so topology can help you a little bit, right? Okay. Okay, so this is all for so these relations that Arnold came up with, or this sort of presentation of this group, is just for the plane, right? So oh yeah, sorry. In space, only one juggling rhythm. Okay. You can ramp that up, right? So you can ask, okay, what about Euclidean space of any dimension? It's actually the same generators. They obey the same relations, and they live in dimension m-1. So these are sort of codimension 1 phenomena. If you look at the dimension of X, it should be in this sort of codimension 1 thing, which sort of makes sense because you think, what are you doing? You're sort of slicing out hyperplanes. So it sort of makes sense. Okay. You can actually do this for X. So Kriege and Totaro did this, actually say independently. This is not a joint paper. They just proved the same thing at the same time. You can sort of compute it in the same way for X being an algebraic variety, but you have to understand that the topology of X itself comes into here. So when you write these generators down, you're thinking of this thing as an algebra over the cohomology ring of X, if that makes any sense to you. Okay. Cool. So what does this tell you? That's Bert Totaro. It says that the configuration space is at least as complicated as the space is a configuration space on. In fact, it's more complicated, which tells you that there's just no way to do this global motion planning thing. You can't just learn one way to juggle and have it work, right? You somehow have to be responsive to changing situations. So I guess that's good, right? It means it's probably hard to train a robot how to juggle. I don't know. All right. So let's take a step back and imagine that instead of juggling ordinary balls, we are going to juggle some magic balls. Okay, these are going to be balls that allow some of them to coincide. So let's say we let the green and the red ball coincide. Okay, or I should say pass through each other. We don't have a problem if they smack into each other. They just keep going. Everything's good. We still want to rule out the red. Yes, the magic balls will become tanks soon. If we want to, we still rule out red and blue, and we still rule out green and blue. Okay, so let's see. There's a couple of ways that you can sort of allow various coincidences. I'm going to record these in in a graph, right? I've got some vertices, I've got some edges saying who's allowed to coincide with whom. So you can either have exactly one coincidence allowed, you could have two coincidences allowed, you could have all three coincidences allowed, right? I left one out actually, which is that you could do what we originally did, which was allow no coincidences. Okay, so this is, I couldn't put this in a poll because it's not like a multiple choice question, but I left one out. So which kind of coincidence did I leave out? Maybe I'll let us all think for like 20 seconds, and if someone comes up with the answer, they can shout it out. So what kind of coincidences could I allow that I haven't already diagrammed here? That's not just one, just two, or all three. Okay, Brian's got a hand up, yeah.
Are all three balls in the same place allowable in?
Exactly, right? So I want to be able to distinguish between the balls having the case that they're not all equal to each other, and one where anything goes. Okay, so I hope this distinction is is clear, right? In other words, I'm interested not just in the pairwise relationships, but also in the sort of ternary and whatever 4-ary and 5-ary relationships among these balls.
Andrew, just a quick question.
Yeah.
So you have the blue, red, and red, green connected.
Mm-hmm.
I'm assuming that that's up to permutation. You just change the color names, and that's why you don't have.
Yeah, exactly.
Okay.
So I actually really there's a ton of them, but they're like
okay.
isomorphic in some obvious way. Yeah. So I guess these are like isomorphism classes. Yeah, and so
sorry, can you clarify so that anything goes in the not all equal? So the not all equal, that means any two of them can coincide, and the anything goes means they can all three coincide.
Yes, that's correct. So if you think about this in terms of, so this picture is happening, this is like the who's allowed to coincide, it says nothing about X. So let's take X to be the real line, okay? So what's the configuration space for the not all equal one? It's gonna look like you take R3, three-dimensional space, and you drill out just that line where X equals Y equals Z. Yeah, whereas anything goes means you don't drill anything out at all. So, okay, so one of the things that you notice about this is if I have one of these sets of permissible coincidences, right? So I give you a list of vertices or a list of balls that are allowed to coincide. If I give you a subset of that, so let's say I tell you these 5 balls, they can coincide. Well, any subcollection of 3 balls of those 5 can also coincide, yeah? That's sort of what coincide means. So what this tells you is the set of permissible coincidences is downward closed. It's closed under taking subsets. And the reason that's exciting is because we got a word for that, right? If I give you a set of vertices and a collection of subsets of that set of vertices, which is non-trivial, it's got to have the empty set in it. Of course, the empty set is pretty clearly permissible coincidence. And that set of faces is downward closed. That's a simplicial complex, right? Okay, so how does this work out sort of in general? If I give you a list of these vertices called sigma, it's just going to be, think about it as like a list of numbers, right? We're just going to number the vertices or color them or something. Then you can think about the corresponding diagonal over in x to the n. So you take the n-fold product, call each coordinate of that x1, x2, etc. Let's say my sigma is 1, 2, 3. Then the corresponding diagonal is the set where all of those indices are the same. So it's like a diagonal, but it's no longer codimension 1. It's going to be much higher codimension, right? In fact, its codimension is k. That's one way to think about it. Okay, so that's a diagonal. So what do you want to do? You want to take your big space x to the n, and you want to cut out all of the diagonals. Well, not all of them. You only want to cut out the ones that are not licensed by the simplicial complex S. So if I give you a simplicial complex, I can recover a space that looks like juggling, except that everything that's in the simplicial complex, those balls are allowed to coincide. Okay, so maybe somebody asked me a question about this definition. There might be an obvious one. Maybe I'll highlight your attention here, which is, first of all, I'm cutting stuff out, but the stuff that I'm cutting out is determined by the complement of the simplicial complex. So it's a little bit grody, yeah. Yeah.
Is there something dual?
Is there something dual? Well, sort of. So it turns out that so this is the set of permissible coincidences. Unfortunately, the set of non-permissible coincidences, that's not a simplicial complex. So like, it doesn't have a really nice, all you can say about it is that its complement is a simplicial complex. So that's kind of the unfortunate thing. It's just not interesting, really. So, what are you gonna do? Okay, turns out we can say a ton of stuff about the cohomology rings of these spaces. So first of all, you can show that this thing is recursively computable. So if you've done any graph theory, if you know the chromatic polynomial of a graph has this thing called the deletion contraction relation, where you simplify the graph and eventually you end up computing this thing. This thing works the same way. You take your simplicial complex and you simplify it, and there's like some long exact sequences and blah, 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 blah. But you can recursively compute this, right? So if you know enough of them to begin with, you can, for simple simplicial complexes, you can build up any one you want to in principle. Very recently, sort of, again, the situation where two people computed the same thing at the same time, you can actually compute this in the same way that Arnold, Kriege, and Totaro did, right? So you can write down an explicit set of generators and some explicit relations that tell you how to compute this cohomology, again, as an algebra over the cohomology ring of whatever manifold you started with. There's another way to think of algebraically computing it as a purely algebraic object. So this Boxset and Manouche, and then me and Radmila made this like, you have to know some geometry to make it work. But in the second statement is just there's an algebraic structure that looks like all of this stuff. In both of those, what I'll say is the generators, where do they live? If I give you a minimal non-face of S, right? So what's a minimal non-face? Did I put a picture? I did, good, okay. So what's a minimal non-face of this guy? This S has no minimal non-faces, right? And this has the minimal non-face just given by the triangle. For this one, it's got two non-faces, this edge and this triangle, but the edge is a subset of the triangle, so the edge is the only minimal non-face. Okay, so it turns out if you write down your minimal non-faces and you look at their dimensions, so this one has dimensions say k, then that tells you where the corresponding generator lives in cohomology. And that's the case for both of these, the purely algebraic one and the sort of the geometric one. Okay, so you can actually compute these, and they're always complicated. Maybe that's the upshot here, right? If we wanted to, we could pick out any particular group and figure out exactly how complicated it was. So I want to make a pitch here for the necessity of this. I'm going to talk about the work in political science and stuff, and there, and in lots of other sort of fields of applied math, there's networks and graphs. Those are the rage, right? People like networks; they like them. The problem with networks is it can only tell you binary relationships. Okay, so I want to make a pitch why we care about higher order relationships. So let's take a love triangle. Okay, so this is Yolanda, Zebulon, and Javier. Okay, and they're in a love triangle. So Yolanda is seeing both Zebulon and Javier. So it's okay for Yolanda and Zebulon to be in the same place at the same time. In fact, that's probably a good thing. It's okay for Yolanda and Javier to be in the same place at the same time. Again, probably a good thing from Yolanda's perspective. It's even okay if Zebulon and Javier are in the same place at the same time. What's the only thing that we have to avoid if we're Yolanda? That they be all in the same place at the same time. Like, that's bad, right? Okay. So, some questions here. Sorry, the point is that the ternary relationship matters, right? So it's not just the binary relationships that you care about. Okay, so there's two questions we can ask. And this is going to be polls 2 and 3. So first of all, we might ask, if we're Yolanda, is there a way to ensure that we can get from a particular date with Zebulon to a particular date with Javier without being discovered? Okay, so poll 2, can we have it now? Can Yolanda get away with it?
Do we care about this? What space we're in?
Aha, excellent. Yeah, so the answer is, of course, it depends on the space, right? Okay, good. You might ask yourself, what about the space does it depend on? Okay, well, it looks like we're about stabilizing it at 2/3 of people say that we can, that she can get away with it, or a little more than 1/3 say no, she can't. What I'm really asking, is X path connected, right? Can I get from one to the other without discovery, right? And so here's the thing, yeah, that depends on the space, right? But if X is, say, a manifold of dimension at least 2, which, you know, maybe the surface of the Earth counts, yeah, no problem, right? So you can get away with it. Okay, now, poll 3, the second question. Can Yolanda get away with it like once and for all? Is there like a single way that she can definitely say, yes, I know the rule, I will always navigate according to blah? Okay, so it looks like we've about stabilized in the other direction. This time the Vox Populi is correct. There isn't a way to just always get away with it. I'm sorry, let me go back. So this is the question of whether or not there's a global motion planner, right? And what do we say about the global motion planners? They only exist in a space if the space is contractible. The thing is, these configuration spaces are like never contractible. Like they're always topologically interesting. So the answer to the second question is no. Like you know, Yolanda just can't do it automatically. She has to be smart. It matters, you know, where these various dates are happening. So, okay. So, so the first question is really a question about path connectedness of the configuration space. The second one is about contractibility of the configuration space. And, you know, yeah, you're absolutely right, Doug. I mean, I think that the solution here is just to have a thruple and be done with it. But, okay, so there was this question about what kind of a space is involved in the first question. And I want to point out that if you're like trying to direct like a rom-com or something, it's probably going to be better to do this on a graph, right? Like imagine a grid of city streets and like people are like running and hustling and stuff. It's probably much more interesting there. And the thing about that is, you know, then the dimension is 1. And so the path connectedness question is now really interesting. That's all I'm going to say about doing this on a graph, because I don't know anything about graphs. I don't know, I have no idea. If you do this on a graph, what happens? I don't know, right? I do this on manifolds, but it could conceivably be very interesting. So for example, if everybody's on a line, like if we're in line land, right? Then this space is definitely not path connected, right? Right? Whatever order you're in to begin with, you're going to be in that order forever, right? There's no way to swap orders. So the only way that works is if Yolanda starts between them. Okay, so, all right. The point here is that a simplicial complex is like a perfect way to encode a higher order relation, right? So let's say that we've got 3 militaries, as happens in Syria these days. We've Russia, the US, and Turkey, right? And they're all 3 of them have their militaries, some military apparatus operating in Syria. What's really bad is, you know, tank operators are tetchy. So if you surprise a tank operator with a tank, that's bad, right? That starts a war. We don't want that. So what they do, even countries like the US and Russia, right, that are really not on friendly terms, they established what's called a hotline agreement. And this is where like a lieutenant colonel or a major or something on one side has a direct line to a lieutenant colonel, you know, some sort of field grade officer, right? Not like all the way up. You don't got to go all the way up. You certainly don't have to go to the respective like foreign ministries, because that would take too much time. And they just phone them up and say, hey, you know, our guys are going to be in such and such place at such and such time. Just don't want to surprise you. We know you're sort of near there, so heads up, right? It's called a hotline agreement. And, you know, that avoids war. How does it avoid war? It allows 2 different militaries to place units what I'll call the same place at the same time without a war starting, right? There's other ways to do this. So for example, NATO, right? I mean, if you're a US military unit and you see a German tank, it's not going to bother you, right? That's just how it is. So, okay, of course, you could imagine having hotline agreements with the other parties, right? So in this case, we've drawn a picture of all 3 possible hotline agreements in place. or if you like, you could draw it as a graph like this. So binary relationships do matter. They matter very much, but they're not the whole story. So I want you to realize that having pairwise hotline agreements is different from having a hot Zoom agreement, right? If they're not all talking to each other at the same time, you could imagine one person trying to relay them, but it's going to get messy, right? So that's a different situation, right? The hot Zoom agreement allows everyone to be in the same place at the same time. You might start a war even if you have all the hotline agreements, right? Because people, like I said, tank operators, they get tetchy, right? Okay. So ternary relationships matter. I'll say it's not just hotline agreements. There's all sorts of other stuff in terms of like international relations. You could imagine like NATO style stuff. You could have a mutual defense pact, a non-aggression pact, status of war. There's a ton of ways to do this in terms of military forces. If you think about on the economic side of the house, lots of international agreements involve economics and free trade. So you can try to understand that an empty triangle's worth of free trade agreements is not the same as having a mutual free trade zone, right? In fact, there's several examples of that, like the U.S. and Jamaica and I don't remember the third country, and sugar. So there's not free trade among all three, but there's free trade among every pair. It's interesting. Okay, so this is a really natural way to encode this kind of discrete structures that people who study international relations are very interested in. In fact, there's a really nice data set of all of the international agreements, alliances, etc. It's like a giant library of all of these, including how long they lasted, who was involved, what the nature of the alliance was. So it's a really nice data set because it's right there. It's like an Excel sheet, and you just can populate what the simplicial complexes look like. Okay. Right. So why do we care about war? Yeah.
Sorry, that would be a simplicial complex that even changes through time, right?
Yeah, so there is this question about what happens over time, right? And how do you understand this? And you should just think it's like the same vertex set, but you get different simplicial complexes at different times. So yeah, again, that's the thing I'd love to understand, but I don't. So I won't talk about it.
Okay, I thought that's where we were going.
Sure. No, but it's great. If nothing else, this stuff could allow you to understand like what happens if you have a certain change in the international structure, right? You could compare the two, right? Maybe you don't know how to get from here to there, but at least you can sort of in a comparative sense say, here's why this war happened and that one didn't, or whatever. Right? Okay. So let's think about why war happens, okay? And there's this, chestnut that trade prevents war, right? We should try to expand our free trade with people so that we don't have to fight them to get what we want. And what I'll say about that is that that's not without controversy. Okay, so the question is conflict evitable? That's one question. Could we avoid war entirely? That would be grand, right? Supposing that's not possible, you at least want to know, how do you discourage war, right? If you're in a peaceful state now, how do we stay there, or do a better shot of staying there? How should we intervene? Things like, should we change the political structure? Should we change the diplomatic structure? Should we manipulate the economy somehow? Right? So these are questions we want to know. Okay, so this is an extremely quick crash course in general equilibrium. I've never taught this, so if anyone has, then my bad if I screw something up. So this is sort of introduced by Valra in the 1870s, maybe. And what it says is this is just a way to understand how is it that we're going to come to an economic equilibrium, right? So we all have stuff, right? So we've got some finite set of goods, we've got a finite set of actors, and we're going to assume that they can trade, right? So normally the goods we just number, right? So 1 through L, but of course they could be anything you want. This last one, this is a blast. This is the promised sandwich that I created just for this talk. That's a bacon, lettuce, avocado, sprouts, and tomato sandwich. They're fantastic. Try it. Okay. So what happens? Everybody starts off with what's called an endowment, right? Which just says for each actor, that person has a list of goods, has a basket of goods, right? So for each possible good, you tell me how many you have. So it's a vector in RL. Okay. Then you have utility functions. Utility functions say, if I consume a certain amount of goods, right, in each of the L slots, then I feel so good, right? This should be monotone in each argument because everybody likes having more ice cream sandwiches right? It's better to have more than fewer ice cream sandwiches, even if you don't really like them. It should also be, though, convex in some sense, because you get diminishing returns, right? The 999th ice cream sandwich just isn't as tasty to you as the first one was. So you have these utility functions. So what's going on here? We're trying to make an equilibrium, right? Everybody's going to trade, right? There's going to be some prices involved. If I'm satisfied with my endowment, then I just don't trade. Otherwise, maybe I trade some BLTs for a burrito or something, right? Okay, so we're going to assume two things. The market's clear, right? The markets have done their work. There's nothing just sitting rotting in the field, and there's a budget constraint. So what does each actor want to do? They want to maximize their own utility, right? That's what utility is. It's the thing you want to maximize. So what you want to do is say how many of each good. This vector xi is a vector in RL. It's how much stuff I consume, right? That's something I have control over. I can decide, what I consume versus what I trade. Right? I don't have control over anybody else, but I have control over that. And the markets have to clear, right? Which means that the total demand, that is, if I add up everybody's consumption and I add up everybody's original endowment, those should be equal, right? I'm not just magicking up new stuff and no stuff is just vanishing. I have this constraint. So that's what it means for markets to clear. The total supply equals the total demand. And I have a budget constraint, which is whatever the prices are, I don't know them, right? Call that vector P. It should be the case that this thing on the left, P.xi, for each price, so the price is a vector, so for each good I have a price, multiplied by the corresponding amount that I have, that's going to give me how much I spent, right? So the thing on the left, P.xi, is what I spent. The thing on the right, P.omega-i, is what I was able to sell my initial endowment for, right? So I can't spend more than I have. Okay, so looking at this problem for a moment, what am I trying to do? I'm trying to maximize a function, and I have a constraint. So this is just a Lagrange multipliers problem, right? And so, Walras gets all this credit, but really he just set up the appropriate Lagrange multipliers problem. Benefit of that is you take a calculus problem and you turn it into an algebra problem, right? You're just having to solve the Lagrange multipliers problem. So that's fantastic. Okay. So why would you do this? Like, why would you want to understand this? Well, you want to understand the equilibrium set, like where do things settle, right? It turns out there's more than one equilibrium. You can understand the equilibria by saying, okay, if I give you a certain endowment, right, call that omega, that's a list of all the endowments, that's going to create a certain set of prices, right? So there's a uniqueness theorem here that says for any particular endowment, that will determine the prices, right? So, the utility functions are fixed, right? So if I knew exactly what everyone wanted, I would understand, and I knew how much I started with, I'd understand what the prices are going to be. Actually, economists, they can't measure utility, right? They have no means of understanding how, of comparing between me and you, which one of us likes ice cream sandwiches more. But what economists can measure is they can measure omega, they can measure the initial endowments, and they can also measure prices. Like prices are really easy to find, right? So the idea behind the equilibrium set is it's going to be a set that we can measure in the world, right? It's a list of tuples, it's a price, comma, sorry, I guess I should think of the other way. I give you an equilibrium, initial endowment, and then I ask what's the equilibrium price of that endowment. So this set of pairs is called the equilibrium set. And it turns out it's nice. It's a really nice set. So this is stuff from the 50s and 60s, which is that this equilibrium set is in fact a contractible smooth manifold. Like it's really, really nice. So I know you're not supposed to prove stuff in a talk, but I'm going to prove something in this talk. Okay, so this equilibrium set is actually diffeomorphic to R to the IL. Where does that IL come from? That's actually just the set of possible endowments, right? So you have I actors, each of which has an endowment of L things. So you need a total of I times L numbers to encode that. So I wrote diffeomorphic here. There's versions of this. It's homeomorphic, diffeomorphic. If you put a Riemannian metric on this sucker, then it becomes isometric, like, okay. So that's cool, right? Okay, let's ramp that up. Where are the tanks, right? We don't have tanks yet. We got to get some tanks in here. So why do you have a military? You have a military to take stuff from people, right? So what I'm going to do is say I'm going to pick a level of militarization. So I'm going to have a number of tanks that I decide to buy, right? Now those tanks, whatever level of tank I decide to buy, it's going to cost some stuff, right? And it doesn't have to cost just burritos. It might cost 3 burritos and a blast, okay? So that's the cost or a vector RL. We also have contest functions. And what the contest function says is, well, supposing that I give so many tanks, then I'm able to intimidate more goods out of my trading partners, right? Or maybe I'm able to intimidate fewer. I guess, the components of SI could be negative, right? Or they might change the trade-off. Okay, so turns out Rob's theorem just says, same shit, different day, right? Same proof. This set of equilibrium, right? So now your equilibrium involve prices, endowments, and also everybody's militarization level, right? Because you get to pick that. You don't get to pick other people's militarization levels, but you get to pick your own. Okay, so again, it's contractible supermanifold just because it's Euclidean space. Not very interesting topologically. Anybody here who knows Morse theory? There's some Morse theory going on in the background here. And the point is that the utility functions are assumed to be convex. So if you think of the utility functions as a Morse function, if you have a convex Morse function that tells you about the space, it's got to be contractible, right? No other choice. So there's somehow some homology floating in the background here. All right, now let's beef this up. So I want to point something out about Carroll's model and for the contest functions and the deployment cost and all that. All this stuff is aggregate, right? It's like how much in total. My militarization is a number, right? But that's not how militarization works, right? It's not just that you have a number and you set a number. No, you pick where to put those forces. So let's do this in the discrete case first because it's easier to think about. You see you've got n sub I forces to deploy. You're going to deploy them at some loci, right? Some places B1 through B, capital B. And at each one of those points, you're going to have how much goods you can extract by intimidating at that point. You're going to have how much it costs to deploy at that point. So what are your deployments? Well, I have a list of B places. I'm going to deploy some forces. So that's just a map from those points to R, or one way to think about it is to say it's a vector in R to the B, right? And this constraint is just that if I add up all the forces, which I can do by dotting with the vector it consists of all ones, I have to get this number Ni. So that's one constraint, right? I have sort of a budget constraint, a force budget constraint. I have local contests and local deployments at each location. I can get some goods, right? And it's going to cost me some goods to deploy there. So all I'm really doing is multiplying everybody by B, right? So that I have to encode the fact that these contests are not happening in aggregate, they're happening at a bunch of different sites. Okay, but your total loot, again, you just add up across all the sites. Your total cost, you add up against all the sites. And what do you get? Well, again, what does an equilibrium mean? Well, what are you trying to do? You want to maximize your utility, right? Where do you get utility from? Well, you get utility from your decisions about consumption. That's this XI. That's what you choose to consume, right? But then also you've got your, your loot, right? You have taken stuff, you've intimidated stuff from people, and so you get a say in that too. You only get to say where you deploy your troops, but that makes a difference. So you add up, that's your new budget is the one with the loot. Again, you have to satisfy that to certain constraints. So if you think about adding up everything that everybody consumed, that has to equal everything that everybody started off with, the sum of that, minus what we all spent on war, right? So the right-hand side is the sum of the omegas minus the sum of the c's. That's like this second term here. That's what was consumed by the war, or by the militarization, I should say. And again, you have to do this subject to a budget constraint, right? You can't spend more than you had.
If instead of looking for the equilibria, so where like all goods are consumed, if instead we look at capacity constraints, so each person can only admit total volume, does all this flow through readily?
I honestly don't know. Okay. I'd have to think about that. I mean, somehow the important stuff of part of this is that you really have to think about who has control over what, right? As actor I, what am I allowed to change, right? Yeah. Like what's my strategy? Oh, sorry, that word strategy brings up this equilibrium here. This is just the calculus way to write down Nash equilibrium. You can think about that for a minute, but that's what equilibrium means, right? It means you're satisfied and you've done the best you can modulo whatever everyone else is doing right now. Okay.
I think I have another question actually too, which is you could think of this as sort of like a process. So you start with one initial assignment and then you iterate through a collection of actions to arrive at this
so it's like playing
equilibrium.
Risk. Yeah,
right.
Yeah. That's how we think about this also. Yeah. So let's talk about that because then now it matters where the deployments are, right? And so now we get into the question of who's allowed to co-deploy, right? Yeah, so, okay, so let's put this together. Okay, I'm gonna ramp this up, and all I'm doing here is taking it from the picture of finitely many discrete contest locations and smearing that out over the whole world. So W here is the world. It's like your geographic description, right? And now instead of a number at each of these finite points, you have a number at the entire on each point of this map, which means that it's just a function, right? So what we're trying to do is optimize our deployment of troops, right? Okay, and so it's sort of the same question, right? How can we maximize this? Instead of adding up to get the total cost and total loot, we have to integrate, but that's it, right? Okay, so otherwise it's exactly the same. So I'm gonna call the equilibrium W, or W sub eq. That's gonna be, if I have an equilibrium deployments, right? So N1 through Ni, each of those is a function, and I wanna look at like their supports, right? So that's gonna tell me where everyone's deployed at equilibrium. Okay, so what W sub eq tells me is how to understand all the deployments that are suggested to us purely for like economic reasons, right? We want to go there to maximize their utility, right? Okay, and the point here is that when we talk about equilibrium now, there's a spatial component to this. All right, so here are some questions. Let's take a look at what W sub eq looks like. So if we've got our world W, right? And we think about a particular point on the world, call it little w. Well, at that little point, all we're doing is doing sort of the classical like arrow de Broglie thing at that point. We have contests that care about that point. We have costs associated at that point. And so you can prove that for every set of initial endowments, there's a unique equilibrium, right, sort of that lives over that point, right? So what that tells us is you actually can find these equilibrium. Each actor has a strategy, right? An equilibrium strategy. So you might ask though, so one question to ask, right, is how the contest at that point sees the contest at this point. If you have 2 points that are close together, how are the contests interacting? That's a really good question. But another question you can ask is, do equilibrium deployments start wars, right? If you're deploying according to what is in your interest, your rational interest, is that gonna start a war? The way to understand this is you take your W to the I, right? So you've got a copy of the world for each actor, right? And you should think of this like Battleship, right? Like in Battleship, there's 2 players, and I have a copy of the map, and so does my opponent, right? So the space of all possible configurations is like, my space cross their space, right? So let's just say we've got 2 actors, right? And each has a copy of W, and then there's these inside WI. There are these diagonals, right? The things that say, if you cross this, you're gonna have a war. So call those the warlike diagonals, right? And so what I wanna know is, well, okay, let's go ahead and write down the supports of everybody's equilibrium deployment. You can imagine that as you vary the initial, as you vary the prices, or you vary the initial endowments, these sets, the support of N2 and the support of N1, are gonna like move along the corresponding copy of W. And so the question is, when you sort of take their product, does that product hit the, does that force you into a co-deployment that's a warlike condition? That's really the question, right? So, this suggests, well, okay, if the answer is sometimes yes and sometimes no, then we want to know, well, how do we manipulate the prices to avoid that, right? How do we, arbitrarily increase people's endowments? That's what foreign aid is. You're increasing that country's endowment, right? So if you can sort of, look at this equilibrium manifold, which is, this nice sort of set of equilibria, maybe it's nice, but W sub S, right, the sort of peaceable configurations, they don't intersect nicely, possibly. Or it's possible they don't intersect nicely. And so that's the question, like, what's the intersection between these 2 open submanifolds of W to the I? That's the question. And because we're building in geography here, I'm saying, okay, let's do this on R2. Maybe you're thinking about the globes, you're doing it on S2. S2 already has non-trivial topology. Maybe you're gonna do it in S2 cross I because you wanna take into account like airplanes, okay? It's a question, okay. And so here's another thing that I think is really important about this, which is, suppose that we're trending toward war, right? So we are on this green path. We've got peaceful equilibria, right? everybody's doing everything they can according to their rational self-interest, you know, prices are changing, whatever. How do you know that you're like, you know, what if you're tending to a warlike configuration, right? So how could we predict that we're about to be at war with someone just because, you know, our economic interest tells us we should be? So the way you want to do that is you want to say, okay, what we really need to do is zoom in on that, right? Like that path that's about to leave the peaceful set and go into the warlike set. We want to zoom in on that and see what's going on, right? How many ways are there to descend into war? Is it always look the same? Are there, you know, ways to sort of get into a small war versus a big war, et cetera? So what we need to do is to compactify. Oh man, I'm so glad you said that, Andrew. So we need to compactify this because, you know, W sub s is always an open manifold, right? If W is a manifold, then W sub s is an open manifold. So what we need to do is ask about its compactification. Which compactification do we need? We need the one about jet space. So the way to think about this is to ask, so what is jet space? It's like the you know, space of possible Taylor expansions. So the question is, as you have a path coming into this, this sort of bad set, you want to know, well, is it hitting it at a right angle? Does it sort of come tangent to it for a while? Like what's the degree of tangency? Is it, you know, quadratically tangent, cubically tangent, et cetera? And so the answer, yeah, is you need to use the jet space.
So,
Fine.
why was it obvious that the compactification was like the right direction to go there? Yeah, I didn't have that intuition, so I'd love to understand like what could have helped me get that one second earlier.
Yeah. Okay. So I mean, you're going to leave the space, right? I mean, that's the first thing is you sort of want to understand what the boundary of this space looks like, right? So one way to take the W sub s and include it in a space that's compact would just be to put it back into W upper I, right? I mean, like, but that's kind of silly, right? Somehow I guess one way to think of it is that like as you're crossing one of these diagonals, somehow the regime on one side of the diagonal is very different from the regime on the other side of the diagonal, and so you want sort of those pockets, those chambers is what they're called. You want to recognize that they're different. So like somehow you want to split this boundary, if you like, and to see the things along here as being part of the boundary of this piece, and a different copy of that as being part of the boundary of this piece. You really want to keep them separate. The benefits of compactification are that you know, we have utility functions, right? And what are we trying to do with our utility? We're trying to maximize it. Well, if you have an open manifold, it's kind of hard to maximize your utility, right? You know, or at least you don't know that it can be done. So that's another sort of thing to think about is conceptualizing these utility functions not as having their domain in some sort of abstract space, but actually thinking of the utility functions as coming from functions on this peaceable configuration space. So I don't know if that answered your question, but.
I think it added some intuition, which is what I was hoping for.
And so if we go all the way back to the first example of 3 points in R, you're like that chops
I can't go back, but yeah, sure. Yeah, go
that
ahead.
chops R3 into a bunch of, I don't know if they're cones, but chambers, sure. And then allowing some things in general, is this like gluing along the boundary? Is that the same kind of compactification you're talking about here?
So it's not quite, right? So the way to think about it is this, and I'm actually going to sort of, you know, mouse over stuff here. So there's a question as to for this particular configuration space, really, the question is are you coming straight at it, right? Are you coming straight at one of the planes, right? That's one possibility. It could be that you're coming straight. What in the world? It could be that you're coming straight to the true diagonal, right? That could also happen. It could be that you're initially coming straight toward this plane and then you sort of curve and end up coming close to the diagonal. It could be that you come along and you're intersecting the diagonal in sort of a way that you're sort of asymptotically tangent to that diagonal, the true diagonal.
There's a big difference between having two balls when you're juggling go smacking into each other that way versus if they just sort of end up falling next to each other.
Yeah, exactly. So if you think about this in terms of balls, you're exactly right. Like it's really rare to have all three collide simultaneously, right? If you think about it in terms of war, imagine that you have, you know, a bunch of different possible theaters where war can break out, and you have like a war between two parties over here and another war between two parties over here, and then somehow the wars get conflated, right? Somehow big wars and small wars are different kinds of things, right? Wars that involve lots of people, like lots of different countries, right? So yeah, question. Is jet space compact? No, it's not. So jet space is not itself compact, but you can use the jets to create a boundary for this space.
So it seems like you came to an end, which means at some point we should all applaud, right?
Yeah, I think that's perfect. If you'd like to unmute and clap. We have about 3 more minutes for questions if people have questions.
I have a question. Do people actually use these strategies in like war, or is this just a mathematical, like an example for math?
Yeah, so I will say that this stuff is, shall we say, not so hot in the political science community. I don't know about, people, government and stuff, but probably even less so there. So Rob and I actually spoke about this at APSA 2019, the American Political Science Association conference. And, somehow manifolds are a little bit rich for most people in political science, it's a little bit rich for their blood. But that's what we're hoping. I mean, so maybe I should say, like, what's the goal of this? I have a lot of questions, right? And I didn't say, here's a theorem. So in the economic equilibrium business, there. Yeah, so this arrow right here, that's Kenneth arrow. That's the same as the, Arrow's theorem involving voting, right? So maybe one of the goals would be sort of a theorem like that impossibility theorem, where you say under certain assumptions about how deployments impact each other and certain assumptions about what these, contest functions look like, how threatening do we perceive each other to be, et cetera, then, either theorem, it is always possible to avoid war, or theorem, it's not possible to avoid war. There will be somehow an inevitable conflict. So that's kind of like where we're going. Again, there's a question as to whether these models are met in reality, and the answer is kind of, well, most likely not. The advantage that I think from a political science perspective of this is political science is sort of split into 2 camps, right? There's like the discrete people, right? Well, I guess there's other, but in terms of like the people who are quantitative, there's the discrete people who study, discrete things, right? And there's sort of the economic side of things where people study, they have a lot of numbers floating around, right? They care about what the prices were and how much it actually costs to extract oil from Iraq or whatever, right? The nice thing the thing that I like is that I'm working with manifolds, and manifolds allow you to take continuous measurements, right? And you're never going to take continuous measurements if you're only working with graphs. So I view it as a sort of nice thing to take this discrete question about the relationships among states. There's a version of this where you can build in economic relationships too, and to make a prediction about what kind of prices you actually have to be, quantitative enough to actually interact with economic data. But no, nobody's using this. I mean, it's new. So.
All right, we've got like 1 second left. Since next week's presenter is here, I thought, Jessica, would you like to give us a brief teaser?
Sure. Actually, I'm kind of hoping that what I'll be talking about is, it's not exactly related to what we talked about today, but this interdisciplinarity thing is kind of a nice theme. And I'm hoping that people who take the course that I'm going to be talking about will be more likely in the future to accept our speaker's work today. So the talk is going to be a shift away from talking math with just my math friends to talking math with lots of friends that are not necessarily mathematicians. I developed my colleagues and I, we've put together a 2-course sequence for a gen ed math sequence for basically anybody whose program does not require calculus. So just kind of talking about how we did it, how we involved people from other disciplines to get questions that were interesting to them, how we took all of those ideas and baked in both problem-based pedagogical approaches as well as group work and discovery learning. So yeah, I'm going to be talking about sort of how we did the development and some of the implementation lessons learned so far.
Excellent. Okay, can we thank Andrew and Jessica for what they shared today?
Yay!
Thanks. Thanks.
Nice.